Hello everyone and welcome to the lecture on the implementation of a DFS or depth first search algorithm. So this algorithm basically explores possible vertices, remember, from a supplied route, and it goes down each branch before backtracking. And this property allows the algorithm to be implemented succinctly in both iterative and recursive forms. So below what we're going to do, this is the notebook that's associated with this lecture. You can go ahead and check it out, but below, the listing of actions we're going to do upon visiting each node is mark the current vertex as being visited, and then explore each adjacent vertex that is not included in that visited set. With that being said, we're going to assume that the graph is in this simplified form. So let's go ahead and copy and paste that here. And let's go ahead and get started with just the basic implementation of depth first search. So what we're going to do is go ahead and start with just a basic function, call it DFS. It's going to take in a graph and then a starting node or vertex. And then we'll say visited is equal to a set, and then we will create our stack, and that's going to be a list with start as the first element in that list. And we're going to say while stack, we'll have vertex equal to popping an item off of that stack, basically that vertex that's in that stack, that node. Remember, we can use those interchangeably. I will say if that vertex is not in visited, then I will take visited, add that vertex to it, and then what I'm going to do is say stack dot extend, and I'm going to do vertex visited, and then I'm going to return visited. So let's make sure this works before we fully break it down. Pass in graph, and let's start at node A. So if we look at the connected components of A, that's going to be this. And there you have it. There's the entire graph. So we've done depth first search. Let's go ahead and go over everything we just did. So in this implementation, we're using basically a stack-like data structure, which is that list, and we're saying visited. So all the visited vertices, it's that empty set. We set our stack equal just to the starting node, and then we'll say while stack, go ahead and pop that vertex off of it. The vertex isn't in visited yet. We're going to add that vertex, and then we're going to say stack and extend it by this term right here, graph at that vertex, meaning if we look at our graph here, it's a dictionary. So at that vertex, that value, it's this set. So let's go ahead and show you what this does. So if I go ahead and say that set minus, let's say, B or something, you'll notice you get a type error. And that's because this is actually supposed to be a set. So remember, this is what we're actually doing. And that's because basically Python's overloading of the subtraction operator to remove items from a set, we're able to add only the unvisited adjacent vertices. So if we look at this again, this is what this line is essentially doing. So graph at that vertex is going to be all the vertices that vertex is connected to, and then we subtract visited. Remember, visited is a set, so it's a set with that particular vertex on it. And then we keep subtracting until we don't get anything, and then we've built out our entire depth first search. So that's really all there is to it. It's definitely a lot simpler than BFS or breadth first search. There's a couple other like implementation methods and functions that you can go ahead and check out in the notebook. So for instance, there's a recursive implementation here you can check out. And there's also, if you wanted to show all the possible paths between two nodes, there's also an implementation for you to check out there. And there's a bunch of resources for you in case you want to read more into it. So definitely check out, especially this first resources. I find it really good. Just goes over DFS and BFS. It's just a little blog post and just goes over, again, basic graph data structure. It's a little more math oriented, but it's still pretty relevant to what we're doing. And then it gives you, again, code for both methods, for DFS and for BFS. So I encourage you to check that out, and then it goes over generalizing too. It's a great link, great blog post, and there's the official Wikipedia links there in case you're interested in that as well. That being said, that's really all there is to it for depth first search. You take in, if we go back here, your visited, your stack, and then take the vertex, pop it off of the stack. If you haven't visited it yet, add it, and then we can just do this extension operation until we keep going, until we've actually seen all those nodes. And that's all there is to depth first search. Okay, go ahead and check out the full Jupyter Notebook for all the notes and all the implementations, but that's all there is to it. I'll see you at the next lecture. Thanks, everyone.